Živijo, tukaj Dunja in
Maruša.
Kje sva? Na temni strani lune, seveda.
Ampak brez skrbi, nisva se pretihotapili tja štani posadke Artemis, še vedno sva na zemlji. Sva pa za vas pripravili novo epizodo podcasta Temna stran lune.
In preden se zapeljemo v to novo epizodo, pa še eno krajše obvestilo. Konec meseca se odpravljava skupaj v Jerevan v Armenijo, kjer bova podcast predstavili na konferenci o komunikaciji astronomije širšemu občinstvu. In ravno zato, ker bo potovanje in srečanje tudi zelo intenzivno, bo naslednja epizoda išla v drugi polovici junija. Za dober uspeh najinega prispevka pa bi vas poprosili, če po poslušanju epizode si vzamete nekaj časa za izpolnjevanje kratkega vprašalnika. Z njim bi namreč radi razumeli, kdo naj jo posluša, kdaj, kaj vas kot publika tudi še najbolj zanima in kako lahko podcast izboljšava. Povezavo do tega vprašalnika najdete pa v zapiskih epizode.
No, zdaj pa o temi tokratne epizode. Odpravili se bomo v zakulisje astronomskih odkritij. Tokratni gost, Eduardo Martín, je pred malo več kot 30 leti sodeloval pri odkritju prve rjave pritlikavke. To so svetovi, ki niso ne teč, ne mrš. Niso zvezde, planeti pa tudi ne. So nekje vmes. No in Eduardo nam je opisal dogajanje iz ozadja, torej kako so prišli do tega pomembnega odkritja in kako nasplošno astronomska odkritja pogosto niso linearna, ampak polna stranpoti. Eduardo trenutno vodi projekt, ki se imenuje Substellar, in ta projekt uporablja podatke vesoljskega teleskopa Evklid. Kot veste, s tem teleskopom raziskujejo temno vesolje, torej temno snov in temno energijo, ampak v Evklidovih podatkih se skrivajo tudi posnetki rjavih pritlikavk in ti nam bodo pomagali pri razumevanju teh skrivnostnih objektov. Ta epizoda pa je posebna in tudi zato, ker je Eduardo moj šef. Tako da sem se med intervjujem pretvarjala, da nič ne vem.
Epizodo sva posneli v angleščini, intervju pa prevedli in ga v pisni obliki objavili torej na spletni strani. Spet povezavo boste našli v zapiskih, spletna stran pa je temnastranlune.si. Omeniva še, da sva se o rjavih pritlikavkah in projektu občanske znanosti že pogovarjali, in to z Tomom Biklom v eni izmed prejšnjih epizod, in sva jo ravno tako dodali v zapiske, ker si jo lahko ponovno ali pa prvič preposlušate. No, prisluhnimo pa sedaj pogovoru z Eduardom Martínom in odkrimo torej, kaj so rjave pritlikavke.
Eduardo Martín is a professor at the Institute of Astrophysics of Canarias in Tenerife. He's one of the pioneers of the brown dwarf research, and he was actually part of the team who discovered the very first confirmed brown dwarf more than 30 years ago. He's currently leading a project by European Research Council. It's called Substellar, and he's using data from the Euclid Space Telescope to identify and study a large number of brown dwarfs in our Milky Way galaxy. Also, he's my boss. So this interview is going to be very special, and I'll ask questions and pretend that I don't know anything. So Eduardo, welcome to our podcast.
Thank you, Marusa, and thank you, Dunia. Glad to be here.
So let's start talking about brown dwarfs. So since I'm not in the field, actually I'm the only one here not in the field, I would like to ask you, what are brown dwarfs? And I know for some reasons that they are called sometimes also failed stars. So actually why they are called like that?
Well, the term brown was coined by Jill Tarter during her PhD. She did a PhD trying to find them in the 1970s. Her supervisor told her that brown was not a good choice because brown is not a color. Anyway, she insisted in calling them brown. At that time, they were often called black dwarfs. They were theoretical entities that had been predicted in the 1960s by the work of the American physicist Shiv Kumar and the Japanese Nakano and Hayashi. So these people realize that there is a limit to the mass of a main sequence star. There is a low mass limit, and that is because quantum effects. When you compress a lot matter, at some point the electrons are free because the matter, when it is compressed a lot, it gets completely ionized, and the protons are occupying a smaller volume, but the electrons try to occupy a larger volume. And there is a limit to that because of the exclusion principle. It's because of quantum effects. Then when you compress too much the electrons, they react. And that force is a repulsion force. It's not the Coulomb force, but it's a stronger force. It's a nuclear force. So this force is capable of stopping gravitational contraction. That means that there is a limit to how much you can compress the core of a contracting star. So stars are able to shine as stars because they ignite the fusion of hydrogen. Hydrogen, the most abundant element in the universe, most of it coming from the origin of the universe. This hydrogen is inside all stars. This hydrogen is everywhere in the universe. So it's the main reservoir of the stars. The stars are able to get to very hot temperatures in their cores because of the gravitational contraction. And when the temperature is more than about 3 million Kelvin, then onset of the strong nuclear force is enough to create from hydrogen atoms fusion into helium atoms. And in the process, there is a little bit of loss of matter because one helium atom has a tiny little bit less mass than the hydrogen atoms that are used to make this helium atom. And because of the famous Einstein relationship between energy and mass, when you convert a little bit of mass, it gets multiplied by the square of the speed of light, which is a very big number. And so with a little bit of mass, you can make a lot of energy. And that's how our sun shines. That's how all stars shine. But as I told you, there is a limit to that. Because as you decrease the mass, as you may form objects that are lower and lower in mass, then they take longer to get to this high enough temperature. And there is a competing effect because they take longer, but they also need to be more compact in their core. They need to get to a higher density because they have a lower mass, and so the weight of all these layers are weighing less. So they need to wait longer and keep contracting, but eventually they hit this limit, this quantum effect, which is called the degeneracy limit, because the matter is no longer behaving like a normal matter. Normal matter, there is the relationship more or less of the perfect gas, that when you increase the pressure, you also increase the temperature. But the degenerate matter behaves in the opposite way, because the more you contract, the more repulsion you get. So instead of heating the gas gets cooler. So once the degeneracy is large enough, and what you create is a degenerate object that never sustains stable hydrogen fusion. Never, and that means it never becomes a star. And that's what you mentioned, a failed star. And that's what Jill Tarter called a brown dwarf. And that's also why people call it failed stars. So you can, these are the most prevailing names for it nowadays, and other little different variations of that, but mainly coming from, for example, in Mexico, the brown color is called café color, so they call it café dwarfs, which I like very much, that term. So I hope I answered your question.
Yeah. So basically, they are formed in the same, let's say, in the same clouds from the same gas of stars, but they are too small to have the same processes in the center. So actually, do not ignite like stars. So they are something that is not even a star, but it's something else.
Something else, yes, something that behaves in a different way than
Mhm.
stars. You can think of this very, very naively. You can think of molecular cloud. These are the big clouds of gas and dust that you can see in galaxies. For example, when you see a picture of a beautiful spiral galaxy, you see a lot of nebulosity. And this nebulosity is the gas and dust where stars are forming. This nebulosity, if it was not perturbed, it will stay there forever. It will never form stars. But there are shocks, there are interactions, and then these nebulosities get perturbed, they get shocked, and they experience this gravitational contraction. They break up. You can think of it like you have a glass, and then the glass is sitting on your table in equilibrium, but suddenly by accident you knock the glass and it falls to the floor. And what happens? It breaks in little pieces. Some pieces are big, other pieces are medium size, but the majority of pieces are very small, sometimes so small you cannot even see them. So this is an example what could happen. The molecular cloud is like a glass floating in space, and then it gets knocked, it gets shocked, and it breaks up. There are a few pieces that are very big. They will become massive stars, which eventually can disrupt everything and destroy the molecular cloud. And eventually, in the longer term, they can even become supernova. But most of the stars are not like that. Most of the stars are small in mass, smaller than the sun, and the brown dwarfs is the extreme tail of this small fragment.
So you said that in the 50s and 60s, they theoretically predicted the existence of brown dwarfs, and then naturally astronomers were trying to find them, and they were looking for them. And then in 95, you were part of the team who actually discovered the first confirmed brown dwarf. Can you tell us a bit more about behind the scenes? How did you discover it? How did you come to this conclusion?
Well, I started working on premium sequence stars. So these are the stars that is the phase between when they get formed until they settle on the main sequence, so fully fusing the hydrogen. In that time, they are contracting gravitationally. So in the beginning, this was my main project for the PhD. But a surprise came. So at that time, when this surprise came, I was working after 2 years in Paris at the Institut d'Astrophysique de Paris, where I started working on this type of stars with Claude Berthoud and Gibor Basri. I moved back to Tenerife, where I'm from Tenerife, so I always keep coming back to my home island. And I started a contract, a 3-year contract to do my PhD in Tenerife to continue it. So I changed subject a little bit because my new supervisor was collaborating with an Italian postdoc, and this Italian postdoc was very interested in very low mass, very young stars. And we went together, the three of us, to an observing run with the Isaac Newton telescope in La Palma. At that time, it was one of the largest telescope in the world. So it was a telescope with a 2.5 meter primary mirror aperture that had been moved from Greenwich Observatory near London to La Palma. And we had a list of targets composed of T-Tauri stars, and there was a TV to acquire the objects. And we thought, because this is a long slit spectrograph, we had a few visual binaries because we thought, okay, if we have a visual binary, then we can move the slit, orientate the slit, get the two objects of the visual binary simultaneously. We can then increase our sample. So we were doing that, and we were pointing at a system that is called a UX tau. This system is a known visual binary system with a separation of about 6 arc seconds, so it's quite comfortable for natural seeing. But that night it was very dark and very good seeing. And the telescope operator, looking at the TV, told us, I think I see a third object there. Is it possible? And we look at the screen and, oh, wow, okay, we did not expect that there was a fainter third object that was kind of between the two known objects, but closer to the brighter one. And we start immediately looking to the in the internet, and we could not find anything. And we thought, okay, then it's something maybe new. So we told the operator, okay, we want to observe this faint object. And we dropped the program. We stopped everything and we start moving the slit. And we did exposures with the align, with the orthogonal, moving around. And eventually the whole night we spent, and the next night. So we got very excited because we thought we had discovered a new object. Eventually, this was not completely true, because we found that there was a little note, not a paper, but a little note in the Herbig Bell catalog. And in this note, George Herbig had noted that on a night of good seeing at the Lick Observatory with the 3-meter telescope, he thought he saw a faint companion to UX Tau A. So he discovered it, but we were the first ones to obtain an optical spectrum for it. And we analyzed the spectrum, and it turned out to be a very cool object. Then we checked the models, and some models told us the mass could be a brown dwarf. It could be below the substellar limit, this limit I told you about, that had been estimated at about 80 times the mass of Jupiter. But not all the models gave us this mass. Some models gave the mass a little above, some models a little below. So we realized it's a brown dwarf candidate, but it was model dependent if it is a brown dwarf or not. But it started us in a new direction. And we also realized that it's very difficult to distinguish a very low mass star from a brown dwarf, because when a very low mass star is very old, it can be quite cool, and the young brown dwarfs can be quite warm. Actually, according to the models, the temperature of the young brown dwarfs and that of the very low mass stars overlap. So just with the temperature, you cannot really tell. You need something else. And we kept thinking about this, and we came up with the idea that because the substellar limit basically is about you burn hydrogen or not, there is an element that burns before hydrogen because it burns at a little lower temperature. So every object that is going to be a star, before being a star, has to burn this other more fragile element in the interior of stars. And this element is lithium. So then we invented the so-called lithium test, and we start to applying it. We start looking and going around the world to Chile, Hawaii, Canaries, using the largest telescopes in the world and searching for lithium in brown dwarf candidates, and we found none, or we could not confirm any brown dwarf candidate in the literature in these years. I'm talking about the years from 1991 to 1994. So we observed all the candidates that we could find. None of them showed the preservation of lithium that we predicted is the hallmark of a brown dwarf. So we come then to 94, and there was an international conference in Garching by München at the headquarters of the European Space Observatory in 1994. And the name of that conference, the title was The Bottom of the Main Sequence and Beyond. And everybody was there. It was really, it was a small community by then. And all the reports were negative. It was a very depressing conference because everything was negative. We reported on the lithium test, everything negative. Geoff Marcy reported on the radial velocity search, and he could not find any brown dwarf, and he put some strong limits. Some theoretical colleagues came with a prediction that brown dwarfs don't exist because they say, okay, then there is too much heating in the star forming cores and this and that, and the limit to the mass that a star can form is above the substellar limit, so brown dwarfs don't exist. And that was the main conclusion in 94 meeting. The next year, the first exoplanet around solar type star was announced. The first brown dwarf in the Plejadah cluster was announced, and the first brown dwarf companion to a nearby red dwarf was announced. Everything 1 year after this depressing conference, suddenly the whole field of substellar objects exploded completely. And we were in this game. We were the ones that discovered the first brown dwarf that has been confirmed in the Plejadah cluster, the first young brown dwarf. It was one of these three discoveries. All of these discoveries were reported in one meeting. It was the Cool Star conference in Florence. I think it was in October of 1995. Michel Mayor and Didier Queloz had the paper in Nature accepted, but nobody knew. Only them, and then also the organizers of the conference and the referees. So they made a big splash in this conference announcing that. We also announced the Plejadah cluster brown dwarf. We had an invited talk there. It was not such a splash as the 51 peg, of course, because we are humans and we are biased. And why we're biased? Because we think it's more important a planet around a solar type star than a brown dwarf in the Plejadah cluster. That's a very subjective thing, actually. But this is because we are interested in the question, are we alone? So the detection of a planet around a solar type star was immediately linked to the search for life, to the big question, is there extraterrestrial life or not? Actually, the Italian press the next day came with Martians and things like that in the cover page. So obviously that was a huge splash. And then in the same meeting, there was a colleague from Caltech that was looking at his portable computer, and suddenly he stand up and start yelling and stop the conference and say, "Oh, a brown dwarf has been discovered around a red dwarf, but in Caltech." And so there was no paper yet, but we got the news that about Gliese 229b at the same conference. So it was really incredible, amazing. So why we detected before anybody else the object in the Pleiades cluster? Well, because we were searching, but we were not the only ones searching. Actually, the Pleiades cluster had been identified as a favorable hunting ground for brown dwarfs, and people like John Stoffer had searched in the early 90s with the deep imaging and found some candidates. Also, people in Hawaii, like Eric Becklin, had a paper with candidates. Also, the British people in Leicester University, Richard Jameson, led by Richard Jameson, using the Isaac Newton telescope, the same telescope that we use for the work of UX Tau and the lithium test, in the beginning of the lithium test. All these teams were taking deep imaging of the Pleiades cluster and searching for faint candidates. But what we did that was different was that we obtained a second epoch, and we were able to measure the proper motion. And that's a crucial part that we had before anybody else. So we reobserved some fields that the British people had observed about 4 years before us. And with that baseline, we were able to find an object that was so faint with the correct proper motion for cluster membership, and so faint that all the theoretical models predicted it should be a brown dwarf around 50 Jupiter masses. So well below the substellar limit. And that was what we did for, we were the first. We were the first to have a proper motion confirmation of a photometric candidate.
Wow, so this is really a priceless insight into how scientific discovery is made.
Well, I have more. There are two things I can tell you that I like very much. First is that I heard from colleagues of Richard Jameson that when he saw the discovery of our brown dwarf, he called his student who had been in charge of analyzing the data, and he told him, "How did you miss that object? Were you drunk?"
Yeah.
So, because that object actually was not even listed in his paper of photometric candidates. They missed it. It was in their images. It was a bit close to the edge of the detector, but they miss it in the photometric catalog that they publish. So that's one funny thing that Richard Jameson. He was a gentleman, actually. I hope he still is. I think he's retired, and I'm not sure about his whereabouts. But he must have been pretty furious that this object was not even in the photometric list of candidates. And the second interesting tale, well, kind of funny, was that the American team of Geoff Marcy and Paul Butler had been searching for planets, and they reported negative results 1 year before the discovery of the Swiss team. Actually, when they realized that there was a hot Jupiter, a Jupiter so close to a solar type star, they analyzed their data and they found two more planets that they could have reported in 94. They had the data, but they had not properly analyzed the data because they did not expect, because of theoretical predictions, that there could be a hot Jupiter so close to a solar type star. So they were collecting data and they thought, okay, in 10 years, we'll look at this data because Jupiter should have a long period.
Mhm.
Wrong. And the Swiss start later and discovered first, but the Americans had the data before them. So that was also a big blunder. And Geoff told me once, well, this we lost the Nobel Prize there, and eventually it's true. The Swiss team got the Nobel Prize and they didn't.
Well, when you were saying also at the beginning, when you were speaking about also the brown dwarf in the Plejadah cluster. The Plejadah cluster is one of the places where to look for young stars that were formed not so long ago. So was this the reason why you were looking at the Plejadah cluster?
Yes, yes. The combination of being young, but not so young that you still have a lot of interstellar extinction, a lot of debris material from the star forming process. The Pleiades is young, but it's old enough that all this gas and dust interstellar has been cleared up, so you can have a clear view in the Pleiades cluster, and also it's very nearby. So it's one of the nearest open clusters. So all this combination made it a favorite hunting ground for different teams. So we were not the first to search in the Pleiades cluster. So I think we were the fourth or fifth team looking there. But we built up on the work of the other colleagues, and we had the idea, okay, about the proper motion confirmation. So this was the key factor that convinced the community this is a real member of the Pleiades cluster, and this is crucial. This is absolutely crucial because you need to have the membership of the cluster, and then you can use the assumptions of the cluster membership to know the age of the object. And the age is the crucial parameter that you need, because the age is what distinguish the brown dwarfs from the very low mass stars. Very old, very low mass stars can look similar to the very young brown dwarfs. So there is some ambiguity there, and we broke this ambiguity with the proper motion confirmation. Then, a few years later, then we also found that in the spectra of the brown dwarfs, there are some indications that you can use to estimate the surface gravity of the object. So not only the temperature, but also the gravity at the surface of the object. So if the gravity is low, then it's a brown dwarf because it's a lower mass and younger. So being younger is a little bit bigger, is still in earlier phase of contraction, and because it's brown dwarf, the mass is lower. So this combination of a young age and lower mass than stars gives you a lower gravity in the surface of the object. And there are some details, some spectroscopic indicators that are sensitive to that. This is something we developed after the lithium test and after the proper motion, and now it's very well also another well-recognized tool to study the properties of brown dwarfs.
Now, if we for a moment think about stars, we know different types of stars. For example, stars that are hotter than sun are blue, and then there's the sun, and stars cooler than sun look red. So we know different types of stars. What about brown dwarfs? Is there one single type, or do we know different ones?
Brown dwarfs are very diverse, just like all objects in nature. Uh, Nature is very diverse. Also, brown dwarfs are no exception. So, with studies of different groups and many people came into the field to study them, and new surveys, new facilities have allowed us to advance in the understanding of brown dwarfs, and to realize that there are indeed different types of brown dwarfs, and to classify them. The community has came up with different ways to classify them and to account for this diversity. So the first thing that was done, and this was in the late 1990s, so this field actually evolved very fast, because from 94, no brown dwarfs, no exoplanets. 95, first brown dwarfs, first exoplanets. Now, in 97, there were already a few brown dwarfs, a few exoplanets, and we started to see that they were different to each other. One of the first things that we realized is that the spectrum of some of these new brown dwarfs was quite different to that of stars. And stars follow a spectral classification that is more than a century old. It's a classification that was mainly done in Harvard by Anne Cannon, and it had stayed like that for about a century. And the classification is the famous sequence O, B, F, G, K, M. So it finished in M, and the M are the coolest stars. Then some brown dwarfs had a different spectrum than M, and it became obvious that they were cooler. And why cooler? Because they are brown dwarfs, and so they don't behave like stars. They can cool more than brown dwarfs. They don't stabilize because of the hydrogen fusion, so they can get very cool. So these objects were cooler than M. And then we check what letters could be available to add to the system of stellar classification, spectral classification. And there were a few candidates, but the letter L was the most obvious choice because of several reasons. And also because it's my middle name, L. So that's only a joke. So we proposed in 97, okay, let's call them L dwarfs. And in 98, we discovered the first L dwarf in the Plejadah cluster, going deeper and advancing more the work that we had published in 95. And then in the 99 came the big breakthrough with the discovery of dozens of these objects, type L, with the two-mass survey led by David Kirkpatrick, and with the Denis survey led by the European people. So we came up in 99 with a lot of new brown dwarfs, and we agreed to call them L dwarfs, and started to do the detailed classification system. A couple of years later, with the deeper studies, a new type of brown dwarf came up, and they were called T dwarfs. And they are even cooler, and they get so cool that in the atmosphere you start to see the prevalence of the molecule methane. You don't see methane in the L dwarfs, but in the cooler brown dwarfs, you see the methane, and the spectrum becomes quite similar to that of Jupiter. Actually, the brown dwarf discovered in 95 around the nearby star Gliese 229 had a spectrum similar to Jupiter, but it was not well understood because it was the only example like that. Then in 2000, more objects came, isolated, free-floating, and they were clearly brown dwarfs of a cooler type than L. Then a new letter was added, the letter T. So in a few years, the century-old system was extended with the two new letters to classify brown dwarfs of L type and the T type. And even more recently, a new letter has been added for even cooler objects that are getting to have a temperature near that of Earth. So they are more or less room temperature brown dwarfs, and they are called white dwarfs. Um, so these are three different type of brown dwarfs. These are the main distinction, but then there are also smaller distinctions. Then because of the chemical composition and other things, then because of the chemical composition, there are other terms such as instead of brown dwarf, then it's a subdwarf, ultra cool subdwarf, extreme ultra cool subdwarf. So that is because then is the dimension of the chemical composition of the objects.
So there are a lot of different objects, and also you mentioned before that when they are forming together with stars, they are forming in a very high number, as far as I understood. So my question is now, how common are brown dwarfs for example, in our galaxy, compared to stars like the sun, and how many of them did you find close to the sun? And the final question is, can they account for part of the matter that we cannot see in our galaxy? So, for example, for dark matter?
They have always been, brown dwarfs have always been a candidate to account for the dark matter in galaxies. Um, the number of brown dwarfs that we have found so far is not enough, not high enough to account for that. But the dark matter is mainly not in the solar neighborhood. The dark matter is mainly spread at very big distances from us. So this is uncharted territory. This is something we don't know yet. We are starting to probe into that thanks to the Euclid space mission. So Marusa is working on this at the moment. This is a very hot topic. We just don't know enough to be able to tell yes or not to this question. So there's still a candidate, and based on the information that we have so far, we estimate they are very numerous. Even in the solar neighborhood, the number of brown dwarfs is quite significant. Is right now is about 20% of the objects in the solar vicinity are brown dwarfs. So the ones that have been discovered are numerous, but not as numerous as stars. But we think this census could be very incomplete. So we have to keep searching and adding more knowledge, more numbers, more better statistics, and probing different regimes of the brown dwarf space. So it's still early. So some things have evolved very fast, and others need more time.
And this is probably why you need also some very powerful telescope as Euclid, right? So Marusha also mentioned before that you are leading a project called Substellar, and that this project is using data from the Euclid Space Telescope. Can you tell us a bit more about the project and what are the main goals of the project?
The Euclid Space mission is probing the dark universe. The main goals of the mission is to study dark matter and dark energy. So these are cosmological questions, and the mission is mapping a big area of the sky, about 1/3 of the sky, particularly the so-called extragalactic sky. So that is the part of the sky where you are farther away from dust. So this survey is avoiding the regions of the Milky Way and also the ecliptic, because they want to go very deep and make a map of the structure of the universe, and use different methods such as weak lensing, for example, to map the structure of the universe and to investigate the nature of dark matter and dark energy. This mission was adopted by the European Space Agency in 2011. And in 2012, the European Space Agency issued an announcement of opportunity for what they call independent legacy projects. And these are projects that, using the Euclid data with a design that is optimized for cosmology, these independent projects should have a strong science case for something related to the goals of the Euclid mission. So I competed for that in 2012 and was selected by ESA for a project to study with Euclid brown dwarfs. Because they are related to the problem of dark matter, and because the capabilities of Euclid are so good to detect many brown dwarfs, more than ever before. So this project then got the position of independent legacy science in the Euclid science team, and this is the position I hold from 2012. And related to that, when Euclid was closer to becoming a reality, despite of several delays, one of them caused by the war in Ukraine, because Euclid was going to be launched with a Soviet a Soviet rocket, but it was cancelled because the Russian invasion of Ukraine. Then that caused a delay. So the situation was uncertain. What will happen? At that time is when I thought it was a good time to propose for funding from the European Research Council to assemble a team before the Euclid started to produce scientific data. And I managed to convince the committees and got awarded this advanced grant from the European Research Council to assemble a team. And that's what I have done. The team is a reality, and we are exploiting the data, and things are going as planned, as they were planning the proposal. The reality is showing that indeed Euclid is the world's most powerful machine to detect and characterize ultra cool dwarfs. Many of them are brown dwarfs. So the distinction between ultra cool dwarfs and brown dwarfs, I didn't tell you before. We call ultra cool dwarf anything that is at the edge of the stellar regime and into the substellar regime. And they may be brown dwarfs or not. In the beginning, the easiest classification is to say, is an ultra cool dwarf or not? And then after we have the ultra cool dwarfs, then we look into more information, more details, to be able to tell, is it a brown dwarf or is it a very low mass star? So these are things that we keep investigating, we keep working on, but we have now better tools than in the 1990s. So we're able to make good progress. So it has been the combination of the Euclid space mission that is an amazing success. It's producing high quality data, and then I was able to have the team in time for this early exploration, this early mining of the Euclid mission data.
So we've seen in the last decade, basically, that in astronomy, we entered the era of big data. We are talking about data mining in astronomy a lot. And with Euclid's brown dwarfs, you also enter the era of big data. And this will, it seems that we are on the verge of big discoveries in the brown field science as well. So what are the open questions? What are the questions we are trying to answer in this field?
The questions are related to the big questions in astrophysics. So the question of the dark matter, what are the contributions to the dark matter? that is related to the number of brown dwarfs in an even lower mass than brown dwarfs. Thus, when you go to very, very low masses, then the brown dwarfs overlap in mass with the planets. And sometimes these are called planetary mass objects or free-floating planets. So these objects could be very numerous, and we need to keep investigating. There are some suggestions from microlensing experiments that these objects could be very, very numerous. So we need to look at that from different angles. So that's one big question, is the nature of the dark matter. Another big question is the properties of the brown dwarfs overlap with that of exoplanets. So it's a mutual learning, beneficial cross information, because with the brown dwarfs we can study the atmospheres of objects that have a similar temperature than exoplanets. And with the even cooler brown dwarfs that even overlap with the temperatures of habitable planets. So we can learn about the properties of these atmospheres, investigate biomarkers. So what is that we could use to have indications that there could be biological activity or not. The brown dwarfs with temperatures in the regime of habitability can be extremely useful to investigate these questions about the mixture of gases. Also, now we see that brown dwarfs are variable in ways that indicate that they could have weather patterns, something like climatology. This can help us to understand better our own climate on Earth and in other planets. So brown dwarfs can be very favored for that, because usually they don't have a bright star so close. Then you can get higher quality data for them. So these are two very important fields: the connection with the dark matter and the structure of the galaxy. The other is the connection with astrobiology. And these are two of the most important questions for humanity in general. So these are really the big questions.
Yes, and we hope that we find or we get closer to these answers soon. Eduardo, thank you. It's been a very interesting interview with all the insight and contexts about discoveries and behind the scenes stories. We learned a lot. So thank you again.
Well, thanks to you. It has been a pleasure to participate and to get your questions. They really bring up a lot of things, and I hope the listeners will be interested in what we say today. Thanks to both of you, and I wish you a very good continuation with your podcast series.
Thank you.
Thank you. Thanks a lot.
Pred nami je mesec maj in tudi seveda kratek uvod v opazovanje nočnega neba in zanimivosti, ki jih bomo lahko srečali in opazovali v maju. Bližamo se torej poletju, kar precej hitro, in temperature se tudi občutno višajo. Nočno nebo bomo v resnici najlepše opazovali sredi meseca, ker bo mlaj nastopil v soboto 16. maja. Začetek in konec meseca pa bo nočno krajino osvetljevala polna luna. Izmed planetov sta najlepša za opazovanje Venera in Jupiter. Svetlo Venero boste lahko opazovali v vlogi večernice, bo nastopila torej po sončevem zahodu na zahodnem delu neba. Konec maja se bo na večernem nebu pridružil tudi Merkur, nizko nad obzorjem. Jupiter pa je še vedno viden v ozvezdju dvojčkov, vendar le v prvem delu noči. In izmed prizorov, ki bojo najverjetneje tudi popestrili vaše večere in bojo vpletali tako luno kot planete, naj predlagam 2 ogleda. Prvi je ob mraku 18. in 19. maja. Takrat bo namreč tanek lunin krajec potoval v bližini Venere in če pogledate nad zahodno obzorje, ga ne boste zgrešili. Ob tem boste verjetno opazili tudi pepelnato svetlobo, ki rahlo osvetljuje temni del lune, kot ga vidimo z Zemlje. Ravno tako pa se bosta Jupiter in Venera pa navidezno na našem nočnem nebu vedno bolj približevala, in to od druge polovice maja naprej do 9. junija, ko se bosta zbližala na razdaljo na nebu približno 2 stopinj, torej če takole pogledamo, je to kar 4 lune razdalje bosta med Jupitrom in Venero. Skratka, en tak lušen prizor za opazovanje. Seveda ob tem naj poveva, da v zapiskih najdete tudi polno zanimivih spletnih strani, torej od preletov mednarodne vesoljske postaje do spletne strani Heavens Above, kjer lahko najdete tudi marsikaj drugega, pa do spletnih strani, s katerimi lahko spremljate tudi sončevo aktivnost. Skratka, ne samo nočno nebo, ampak tudi sonce in dnevno nebo. Skratka, vse to vama priporočava v ogled in seveda tudi v opazovanje. Z vami sva bili Dunja in
Maruša.
In to je bila že 56. epizoda podcasta Temna stran lune.
Nasvete in vprašanja sprejmeva na naslov podcast pisano s k-jem, torej podcast.temnastranlune@gmail.com. Poiščete pa naj lahko tudi na družbenih omrežjih. Podcast je praktično povsod Temna stran lune, pisano vse skupaj in brez presledkov.
Če želite, lahko podcast podprete, in to na spletni strani ko-fi.com, torej ko-fi.com, poševnica Temna stran lune. Hvala vsem, ki ste to v preteklosti že storili in še boste. Nabrani prispevki bodo služili nakupu opreme od mikrofonov do slušalk.
Podcast je del mreže aktivnosti zavoda Kozmolab, ki se ukvarja s promocijo in popularizacijo astrofizike. Hvala Peliju iz sosednjega podcasta, opravičujemo se za vse nevšečnosti, ki je prispeval glasbeni uvod in zaključek.
Slišimo se torej kot napovedano v drugi polovici junija meseca, tako da uživajte v nočnih opazovanjih. Srečno!